we are done with the method of moments, and now we are going to find out the maximum likelihood estimator in case of different distributions that we considered in our theory part. So for this, let us begin with the uniform distribution. So let us consider that same uniform 0, 8. Okay. So here we will import your numpy, and let me just write import numpy as np. Then we also need from scipy.stats, we will import uniform. In addition to these, so these two we imported initially also for method of moments. So since here we are going to deal with the maximum likelihood estimator, so from scipy.optimize, so basically which is used for optimization, from here we are going to import minimize. This function basically helps you to find the maximum likelihood estimator. Okay. So now again we can write np.random.seed as 0 over here. Next we are going to generate a random sample. So let me first write true theta over here. True theta over here, as we have considered initially also, let it be 8. And here sample size is 100. And the data sample, that is the variable which stores your random sample that you are taking from this uniform 08. So it will be uniform.rvs. Again we are using the same steps over here, and scale would be your true theta, and size would be the sample size. Okay. If you can recall the MLE for uniform distribution, when you have uniform 0 theta, so it is basically the largest order statistic, that is x ordered n, right? So here we can use this max function over here, so which will calculate the maximum value for in the data sample that you have generated over here. Okay, so if you print this MLE, print MLE of theta, so this one would be MLE theta that we have obtained here. So we can probably specify the formatting up to 4 decimal places. So what you obtain is 7.907. Okay. So original theta was 8, and here since we are using MLE, so we have taken x ordered n, so which is basically 7.90. If you go above in this one method of moments, we obtained your estimated theta was 8.02. So a bit of overestimation is there in your uniform distribution case for the method of moments. Okay, so because here you are obtaining 8.02 and in this case it is 7.90. If you change this, suppose maybe let us make it as 200, so it will be 7.99. Okay, so you can see that how close it gets to the true population parameter. And we will see also later that MLE is a better method of estimation because it has certain properties. So in that sense you can see that x ordered n is a better estimator whenever you are drawing a random sample from uniform 0 theta. So the next distribution we have is your normal distribution. So normal, let us suppose the parameters over here are same as 5 and 2. So in this case also you can see that for normal distribution, whether you use method of moments or MLE, the estimators that you obtain are same because it is x bar for mu and you have n minus 1 over n s square. That is a sample variance. Okay, so the steps would remain the same more or less. So here we will just be importing the essential libraries. Okay, so import numpy as np, and from scipy dot stats we will import norm. Okay, so we can use this random seed over here. Let the true mu in this case, so probably we can take something else to show you. Suppose mean in this case is 10 and sigma is 4, so true mu let me take as true 10 and true sigma as your 4. Okay, so it means it is not 4 in fact, nor mu sigma square, so that will be 16 in this case. Now you are going to generate a random sample of size 100 and data underscore sample. This would store the random sample that you will be generating from normal. So norm.rvs, so here location would be your true mu, true underscore mu, scale would be true sigma, and size would be sample underscore size. Okay, we can again calculate the sample mean and the sample variance. So sample mean, for that we need this numpy's mean function, so this would be in this way, and sample variance np dot where sample data sample we can write, and also we need to specify that it is going to be your sample variance and not the population variance. Okay, finally your estimated mu in this case would be just the sample mean that you have now obtained above, and because mu hat is x bar and your estimated sigma would be sample size minus 1, n minus 1 over n. So if you want to write this sample size, instead you can find the length and use n. So let us see if I just write this one only. So sample size n minus 1, right, divided by the sample size again, and this would be multiplied by your sample variance. Sample variance, that is VAR. Okay, so let us see what are these values over here. Estimated mu comes out as 10.23. Okay, so original one is true 10, and your estimated sigma is 16.25. Okay, so you can see that again it is close to your population parameters. So this was about your normal distribution. So we have seen uniform distribution, normal distribution also. So the difference is in uniform, because normal distribution both the methods give you the same result, so you can use them. Now the next distribution is your gamma distribution. So let us suppose here gamma with 3 and 2 alpha beta. So here we are considering shape and rate parameter. Earlier for method of moments we considered shape and scale parameters. Here let us see if we deal with the rate parameters. Although we have not studied that this estimation method for gamma in your theory part, but let us see how it is done here. It is better, it would explain you in a better way. So for this we need certain libraries. Import numpy as np, and we need from scipy.stats import gamma, because here we are going to deal with the gamma distribution. In addition to these two, we need the minimize function from your scipy's library scipy.optimize, import minimize, okay, np.random.seed, okay. Now your true alpha and beta, let us define. So true alpha in this case is 3 and true beta, so alpha over here is the shape parameter and here we are taking beta as the rate parameter, okay. Now we are going to generate a random sample of size 100 and a data sample would be generated now from gamma dot do variables. A would be your true alpha and scale over here is 1 over true beta because that is the rate parameter there, okay. So let me just mention that this over here is your rate parameter and this is your shape parameter. So that is why here it will be true beta and size would again be the same, that is the sample size. So after this, now we are going to define a function that is negative log likelihood for the gamma distribution. So let me define that. So define negative underscore log underscore likelihood. We are going to define this negative likelihood log likelihood function for the gamma distribution. So this function takes parameters as params here as input and the data is this data, okay. Here after this we are specifying alpha estimate, so alpha estimate and beta estimate would be basically this params over here. Next what we will do, we will calculate the negative log likelihood function by using gamma.log PDF. So let me write that this function would return minus np.sum. So here we will write gamma.log PDF, in bracket it would be data comma alpha underscore estimate scale is equal to 1 divided by beta estimate, okay. So here what we are doing is that this function basically first of all takes these two as the input and then it calculates the negative log likelihood by using this gamma.log PDF to compute the log PDF for each data point that we have over here, okay, and then it would sum up these values with a negative sign. So this function basically that we have defined over here, it will be used in the optimization process to find the MLEs. Now with this function we can finally find the MLE. So let the initial guess be 2.0 and 1 because these are the initial guess, okay. So let me just mention these are the initial guess for the optimizer. Okay, and now the result would be, so we'll use this minimize over here, minimize negative log likelihood, the function that we have defined initially, then initial negative log likelihood, initial guess would be there, okay. So we are using the minimize function to find the MLEs. So it is going to minimize this negative log likelihood function with respect to the parameters alpha and beta. Okay, and we will specify this args parameter over here, which is basically used to pass the data sample into the function. So args will be data underscore sample, this one that you have over here, data underscore sample, comma, and after this you will have your estimated. From this we are going to extract the estimated values of alpha and beta. So estimated alpha and estimated beta is the result dot x over here. Okay, so if you want to see estimated, what is estimated alpha, so here basically after the optimization is done in this step, you have extracted the estimated values of alpha and beta from this result object that you have created. Okay, and these are the basic MLEs of the gamma distribution. So let us see what is this estimated alpha. So it is 2.86, so the original one is 3, and let us see what is your beta. It is 1.87. Okay, so again it is very close to your population parameter, that is 2. So in this code, basically what we have done is we have taken a random sample over here from your gamma distribution, then we have defined a negative log likelihood function, and we use the minimize function to find the MLEs of the gamma distribution parameter. Okay, so the estimated values would be close to the true values when you are having a sufficiently large and a representative sample. Okay, so for Poisson distribution you can use the same thing, because here also we had lambda hat came out as x bar only, right, in both the cases. So the steps would remain the same, and you will find that lambda hat comes out as x bar. So we can skip that, and instead we can consider your binomial distribution. Let us consider that x is following basically your binomial NP. Suppose n is known to us, so n, let it be 10, and p is unknown. Okay, so for this we will import, so here we just have a single observation. Okay, so import numpy as NP. Next would be the observed value. So x, suppose the number of success is 3. Okay, because here x in binomial distribution, the random variable basically represents the number of success in n independent Bernoulli trials. So in 10 trials, how many success are there? So suppose you know that it is 3, and n we have taken already, n is 10. Okay, so the MLE in this case, when you have a single observation from binomial, MLE would be nothing but be x by n, because if had it been xi, so it would be summation xi, because x, this binomial is there, right? So basically binomial distribution is a generalization of Bernoulli, so it means you have x1, x2, xn coming from Bernoulli. So in this case, in Bernoulli distribution, if you can recall, the MLE was the sample mean, that is summation xi by n. So summation xi is basically x here, because x is binomial, so we can have just this. So you can now print this MLE of p here. This would be MLE here. MLE underscore p. So it is 0.3. Okay, so p hat would be, obviously because it is x by n, so 3 by 10, it would be 0.3. Okay, so this basically completes your 6th week, where we focused on 2 different methods of estimation, specifically point estimation, that is method of moments, and maximum likelihood estimation. And in the next week we will use unbiased estimation to see what are the properties of this estimator. Okay, thank you.